Okay, and then is this on? Yes. Okay, so it said if the population started at 105 insects, and we wanted to find a population after 0.2 months, what would make sense here in terms of which constant rate would make sense to use as a pretend rate, right? As a pretend rate. So is it 20, 45, or 60? So in the first 0.2 months, does it make sense to look at, to say that we're going to use a constant rate of 20? No, because the rate starts at 30 and then it ends up somewhere close to 60. So what about 45? So 45 is something of a middle value, right? It's something in the middle. So if it starts at 30, ends at 60, maybe 45, constant at 45 for that whole time period is a good way to kind of pretend that's what the rate is, right? And why do we pretend a constant rate? Why do we use a pretend constant rate?
To estimate.
Okay, and why can't we just estimate with the actual rate? But why can't we just estimate with the actual rate? Yeah.
There's seemingly infinite rates within that.
Yeah, as soon as a little time goes by, the rate changes, and so how do we do that? But we know we've got the easy math of constant rate of change that we can use. So we're going to come in here and say, all right, for the first 0.2 hours, we'll use a constant rate of 45. 60? What about 60?
Never even reaches 60.
Too high, right? It never gets as high as 60, right? So if you had the three choices of what would you use to pretend this rate would be, 20, 45, or 60, 45 is the third choice, right? Because it's something in the middle of all the rates. Okay, so then this last problem says to devise a way, and notice, I know that oftentimes area is emphasized. We're not emphasizing area, right? So we're not making rectangles. We're making a pretend rate function, a function based on constant rates that's trying to be this one. Based on constant rates. That doesn't involve any vertical lines or rectangles. Okay? That means we're just trying to reproduce this rate graph. Okay, so for the first month, we want to try to estimate what the population would be at 1 month. So just taking this, I can't get in between there. So taking this lead of the 0.2, so I didn't give you, I didn't tell you what interval widths to use. So you could use 0.2, you could use 0.1, 0.3, anything that's kind of convenient. So I'll just go with 0.2, since that's what that previous question asked about, and we'll start with this constant rate of 45. Okay, and so then from 0.2 to 0.4, it goes from something like 60 to something like 30. Again, middle value from 60 to 30, 45. So we could use 45 again, or just, well, for kicks we'll use 40, something different. Okay, and then from 0.4 to 0.6, it goes from something like 40 to 15. Middle value, make it easy on yourself, 20. So what did I say? I said this one was 40, and I said this one was 20. Okay, everyone could have something different. So we could have 20 different solutions to this problem that are all in the ballpark. But the point is, you're making a pretend rate function out of constant rates over some intervals. So 0.6 to 0.8, call it 15. And 0.8 to 0.1, call it 25. So that's just what I'm seeing, just doing it real fast here. Is that something similar to what you did? Okay, and then why do we do this? Why? Because with constant rate of change, we have this very easy way to calculate total amount of change. And what is that? How can we calculate the total amount of change with a constant rate?
That's one. It's
K delta x, right? It's just that we have, how many in this case? We have 5 constant rates. So we're going to have 5 of these, and then what are we going to get the total? And so through here, the population is decreasing, right? What's the population doing through here? It's increasing.
Less at a decreasing rate.
Yeah, but just increasing more slowly as time goes by, right? So that's increasing, but more slowly. So, does the bug population ever decrease here?
No.
It's always increasing because the rate is always positive. Okay, so the rate is always positive. And what do we see about the flag example? That rate of change was always, remember? Negative. Remember, the rate was always below the x-axis, so the height of the flag is always decreasing, right? Okay, so then we can just use this principle of, with a constant rate for 0.2, what was that? Is it months?
Yes.
Yep. So we got K1 delta x plus and we're going to get the amounts of change based on these constant rates, and then what will we do? We'll add them all up. So 45 times 0.2, 40 times 0.2, all the way to then 25 times 0.2, and whatever that turns out to be. Okay, questions on that? So will that be the population, our estimate for the population at 1 month?
No.
Why not?
We haven't added our initial value.
Yeah, so this is just amounts of change, right? These are just amounts of change in the population each 0.2 months. So then we'd have to get the actual population estimate would be, was it 105?
Yes.
Okay, now before I write this, I wanna look at this right here. And notice that what are we doing? We're just writing the same thing over and over again. So if we had 10 of these or 20 of these, it would intervals, then we'd keep writing the same thing over and over again. So we have a shorthand way of writing a sum where you keep summing the same type of thing over and over again. And so that's this symbol here. Or that's Greek sigma, right? And what does Greek sigma mean? Stands for sum, right? So we're going to sum up a bunch of things that look like this. They're all k delta x. It's the only thing that changes is the value of k. So we'll just let I be the index, and then I will go from, and we'll let I be the interval number. So this is the first interval, second interval, third interval, fourth, fifth. So I will go from 1 to 5. So this is not meant to be scary. It's meant to save us the time of writing out all these things over and over again, because they're all the same. So if they're all the same, let's just write it once, and then have this symbol means we're going to add them up. Add up 5 of those. So our population estimate is going to be the 105 plus the sum of the k delta x's, in this case 5 of them. If you did delta x of 0.1, then you'll have 10 of them added together. Everyone could have something different. So then the population estimate will be 105 plus our estimate of the change based on constant rates that are trying to be the actual rate function. Okay, anybody have a question on that? Or this new notation, please?
I understand the utility in having your delta x be standard, like a consistent interval, so we can use that notation.
Yeah.
But we don't necessarily need to, right?
Delta x could change.
Right. We could have larger and smaller intervals.
That's right. That's right. Yeah, you could have the first one be 0.1, and the next one be 0.3, and the next one be 0.08, and then the next one be whatever.
Just to ease your estimates. If you
Yeah. So this lends itself to, I mean, you could factor out the 0.2 after you
Right.
understand that they're all times 0.2. You could factor out the 0.2, then to make it easy, you could just add these 5 up and multiply by 0.2.
Sure.
You couldn't do that if you had different size delta x's. You'd have to do them one at a time. Other questions on this homework? Anything? Okay, so we're in this journey here of making sense of the fundamental theorem. So let's just look at this slide right here. And so let's add this to the mix here. What does this do? It calculates an amount or an amount of change. Okay? So it calculates an amount or an amount of change. And principle 1 was constant rate of change. That if you have a constant rate of change, the amount of change is the constant rate times your amount of your change of your independent variable. So, if you're going 70 miles per hour, everyone gets this. If you're going 71 miles per hour and you go for an additional 1/2 hour, what does delta y calculate? What does it calculate then?
It's the
Miles.
distance.
Yeah, your change in distance. For this change in time at 70 miles per hour, constant rate of change, you will go an additional 35 miles. Right? So easy principle, but we got to make sure that we're good with this notation, right? So, or if gas is $2.65 a gallon, and you put 10 more gallons in your tank, what does delta y calculate, and what is its value? What does delta y calculate, and what's its value? Sir?
The cost of the additional 10 gallons.
Yeah, which would be what? How much?
26 plus 5.
26,
$25.
50, right? Right? Same thing. So it's constant rate of change, right? Constant rate of change. Crucial for the fundamental theorem. Second is that lots of things in the world are modeled by a constant rate of change. Instead, they're modeled by a changing rate of change. So realistic rates are usually changing rates, especially speed. Okay, speed is the rate of change. Usually, that's a changing speed. Okay. All right. So this was the speed of the flag, the rate of change of height with respect to time of our flag. Okay. Principle 3: make a pretend rate function out of what kind of rates? Make it out of changing rates?
Approximate average rate of change.
Constant rates, okay? So yeah, so we're gonna make a pretend rate function out of constant rates of change. Why? Because we want to use this. We want to use principle 1. If we don't have a constant rate of change, we can't use principle 1. So that's why we turn a changing rate function into a bunch of constant rates so we can use this real easy math relationship. So we mimic the rate function with constant rates, and we can apply principle 1 and add up the changes to estimate the total amount of change. And then the total change is the sum of a bunch of k delta x's, right? All right, so next idea here, next principle. So let's look at our flag again. Here's the rate of change function, the realistic one. Okay, so we talked about finding constant rates that are trying to be the actual rate. But there's some more kind of systematic methods. So that's a nice that's a nice way to think about it and get the idea of it. But if we have lots of intervals, we want a systematic way to get these constant rates fast. And so one way to do that would be what's called a left or right side approach. So let's talk about a left side approach. So rather than looking at a certain interval and saying, okay, here's kind of the middle value, and then going in and here's kind of the middle value, that's fine, but it's kind of takes a long time. A left side approach says, look at the interval, and for the constant rate, use the actual rate at the left side of the interval, or at the starting value of the interval. Let me say it again. So we're going to, for a given interval, to get the constant rate, rather than eyeballing, we're just going to pull off the actual rate from the changing rate function at the left side of the interval and make that the constant rate for the whole interval. So let's do intervals of 0.5 here. What is the actual rate at the left side of the interval here, of the first interval from 0 to 0.5?
0.75 or something.
I had heard 0.6 and 0.75. So where's the left side? Is it 0 or 0.5? 0. And what is the actual rate at 0?
0.
Is it 0? The actual rate of change?
Negative something.
Do you remember what it was? Negative 0.75 was what this was all based on, right? Negative 0.75. So at time equals 0, the rate is negative 0.75, and so we're going to use that one actual value and make that the constant rate for the whole interval. So what does that look like? It looks like this. Kind of. Should be horizontal. Okay. And then the next interval from 0.5 to 1. We want to look at the actual rate of change based on the changing rate at the left side of the interval and use that for the constant rate. What is it? He wants negative 0.4. Yep, so at the left side of the interval, at 0.5, it looks like about negative 0.4. So then that's going to be our constant rate for the whole interval. So this method kind of takes the guesswork out of it. Okay? It takes the guesswork out. It's just kind of automatic. It's like, okay, go to the left side of the interval, get that rate, constant rate. So there's no eyeballing, there's no estimating. Okay? How about from 1 to 1.5? What will we have? From 1 to 1.5.
Negative 0.75.
Yeah, it's back here. See, at 1, it's our pretty close to negative 0.75. So we'll just call it that. All right. From 1.5 to 2.
Negative 0.75.
Again, so from 1.5 to 2, the rate of change at the left side is, again, negative 0.75. Okay, what about from 2 to 2.5? Somebody knew? From 2 to 2.5, what would our constant rate be? Negative 0.01, okay, something like that. Just a little bit below 0. Exactly. All right, so this is a left side approach. And then a right side approach would just be look at the final x value of the interval, get the rate of change there, and make that the constant rate for the whole interval. Okay? So then there's likewise, and then you can do the mid approach, which would be find the actual rate in the very middle of the interval and use that to be the constant rate for the whole interval. Okay? And these should be familiar from Calc 1. So now for a given rate function and a given interval and a given approach, then we'd all have the same, if we did it right, we'd all have the same thing. Okay? We'd all have the same thing. If we chose 0.2 as our interval width and did a right side approach from 0 to 1, we should all get the exact same constant rates, pretending to be the rate function. Okay? It's very systematic. There's no thinking or guessing about what those rates would be. Yes, sir?
For these types of functions, is there an approach where you would take the rate of change at the beginning of the period? Just like look at every cycle and then just factor it out?
Except that then, if you did that, then you just have a constant rate the whole way, and you wouldn't be taking into account the cycle, right? Because you get the same value.
Right.
If you start every time you start with the cycle, you have the same function value. So if you keep it, then all your constant rates will just be
So
one.
why doesn't that work? I mean, I understand that, but like.
Doesn't work for that reason, because you only get one rate. If you take it at the beginning of the cycle, you're just going to get one constant rate the whole way. You're going to miss out on all the other rates in between, where that's actually going through the cycle.
Sure. Maybe that only works when it crosses the x-axis, like when it's reflected above the x, because then you have they subtract from one another, the population values, or whatever it is, or y.
But even if it crossed the x-axis, you said you're going to take it at every time the period starts again, right?
Like, let's say we have just straight up cosine,
Right.
and it's reflected about the x, and so you have like this area of value canceling out this other one that repeats.
But
Does it work?
yeah, because you're going to have a positive rate, you're going to increase, and then you're going to have decrease, and then you're going to increase, and you're going to decrease by the same amount. But if you take your endpoints to be where the cycle starts over, then you're going to get the same rate. You got to make the interval smaller than the period,
Okay.
or else you're just going to get a constant rate, because at the start of the period you're going to have the same function value.
So the interval has to be smaller than the period.
Smaller than the period. Yeah.
Gotcha. Okay.
Yeah. It's like if we did the period here, and say we started here, then we're going to have, what's our constant rate going to be? 0. And then we're going to do the next one, the next period. 0, 0. So the rate would just be 0, right?
Yeah. Okay. Thank you.
Yeah. Okay, so if I were to, let's graph this a little more formally here. What did I say here? Point. So let's do 0.5. So here's actually what it would have been. So this is now a nicer computer version of what we just tried to do. Okay, every 0.5 using the left-hand approach. How is that doing at pretending to be the rate function? Good or bad? We're stumbling on our next principle here. Is that doing a good job of pretending to be the actual rate function, or a bad job? Yeah, so when you just look at the constant rates, there's no way you can tell what the changing rate function is supposed to be. It's good in the sense that it's mostly negative 0.75. You see lots of them are negative 0.75, and we know that that's what most of the function is. But in between, it's not doing a good job at all. So the question is, how can we get a better pretend rate function? Everybody knows this, right? Yeah. So smaller intervals, right? Smaller intervals. Okay, the question is, why do smaller intervals give us a better pretend rate function? Why do smaller intervals? Give it a shot, yeah. More rates of change. That's what we're saying. So why does more rates of change give a better pretend rate function? Yeah.
You have smaller, more accurate increments.
Okay. Matthew, you're saying?
It becomes more exact.
How does it become more exact?
As it becomes smaller, it becomes smaller to the actual rate of change function.
Okay, yes, exactly. Yeah, what are we saying?
We're eventually just going to map our f. Like if we have
But-
infinitesimally small.
Right, I'm asking why. So why do smaller intervals result in a better pretend rate function?
You're measuring instant rates of.
Not instant yet. We're not there yet.
Always.
Just a smaller interval.
It's just becomes small to the point that you can't tell it's different from the actual one.
Okay.
Yeah.
Includes more portions of the functions, more to the general area.
Okay. Yeah. So kind of
All the functions.
putting it all together, All I'm talking about is smaller. So some of you guys are jumping to like super small. We'll get to super small. I'm just talking about smaller. So if we make it a little smaller, here's 0.2822 is my interval width. And here's 0.1634.
You're dealing with more information.
Right, you're taking more rates on smaller intervals, and so here's 0.0446. Now we're talking, right?
Yeah.
So with smaller intervals, the pretend rate function does a better job mimicking the rate function because it's taking more and more rates. Taking more and more rates, it does a better job mimicking until we go really small here. Here's 0.005.
Wow, that's beautiful.
All right, beautiful. Okay, so again, you're looking at a bunch of constant rates here. It's just that the interval is super small. And because it's super small, those constant rates are doing a really good job of pretending to be the actual rate function. Versus that, right? So you can't even see the steps anymore. Just the steps is like a perfect match to the actual rate function. Okay, so that's the next principle about this, is we're going to take super small intervals, well, smaller intervals, and then if we want something that's really, really close, then we just take super, super small intervals, and lots of you were saying that. So this is the idea of very, very small intervals. Creates that rate function almost indistinguishable from the rate function. Okay? Almost indistinguishable. If I made it any smaller, you wouldn't be able to see. It would just be, it'd be so faint and dust you wouldn't be able to see it. Okay. How do I to the next page? No, that wasn't it. Okay, so principle 4 is make more smaller intervals. Better pretend rate function, better estimate of total amount. And we're going to keep going down that path because we want to get the actual, recreate the actual rate function. So principle 5, super small intervals means exact amount. So we're talking about now adding up all the k delta x's to get the amount of change, the total amount of change of whatever y is, right? But now when we embark into the land of super small intervals, these delta x are really, really small. What does that thing become? So this is the meaning of integral. When things get super small, the sum of all these k delta x's is expressed this way. Did they teach you this? Yes. Hopefully they did, right? That's what this integral f of x dx is basically identical to just summing up a bunch of little, lots and lots, a zillion changes, all calculated by k delta x. So let's see, how are they the same? What's one thing that's the same about both of these in the symbols? Can you tell me? The sigma? Okay, yeah. So notice that we've got Greek sigma is the same as what? And what is it the same as over here? What's that? This thing? Are you looking at this thing?
Yes.
Okay, so this is Greek sigma, and this is a German S. So Greek sigma and German S, they both mean sum. They both mean sum. Tell me something else that's the same about both. Brock,
Delta x.
tell me something else that's the same about both these expressions.
dx is just an infinitesimally small delta x.
Right, so delta x is like a finite or relatively large change in x. Dx is then a super small version of that. So there's our delta x, and then that's analogous to dx. Dx is just super small version. Okay, what else is the same? Yeah.
K relates your y to x, like f of x does.
Okay, and what is k again?
The rate of change.
Yeah, so here, over here, we had discrete rates of change. We had k1, k2, k3. But then if the intervals get super small, then it's kind of like we're looking at every possible rate, right? And that's the function. That's the rate function, right? So instead of discrete values of rate, we have the continuous rate function, because if you change x a little bit, if you do a little dx, well then you get a slightly different rate. And then you keep changing x, so you're going to get the continuous flow of all the rates instead of these chunk rates, right? So they're both saying, summing up a bunch of k delta x's. It's just on the right, it's just a gazillion of them that are super small, right? Okay. And then a and b, what are those? Are those k values, x values, y values? What do we mean by a and b? Yeah?
There are bounds.
Okay.
Into when we're going to analyze the
So are those
function.
k, those bounds of k? Are they bounds of x? Are they bounds of y? What are they?
Well, you're supposed to be looking at bounds of x and how you set your coordinate system.
So yeah, so according to this, they would be x values, right? So starting at x equals a and ending at x equals b. So that doesn't come through in this notation over here, but it's implied, right? There's somewhere we started with the first interval, and there's somewhere we ended with the last interval, and so that's we're showing that here. A is the start of the first interval, B is the end of the last interval. But now we just have like an infinite number of intervals in between. Question?
So would it be that where we start accumulating and we accumulation?
Yeah, so one way to talk about we're calculating the total amount, you can think about that as accumulation. We're accumulating whatever this amount is. So we're accumulating bugs, number of bugs in the population. Or we're accumulating the height is kind of accumulating, it's decreasing, but we think about the accumulation of bits of height as it's decreasing. Okay. Questions on that? So this is, but we're only talking about the left side, right? So we've made it to principle 5, so the 5 principles that get us to the left side of this thing. So now I want to talk about the right side. Any questions on the meaning of integral? Like I said, we're going to be doing integrals. It's going to be 70% of the course, so we need a good concept of it if we're going to be dealing with them so much. Any questions? Okay, so let's go back to so let's look at the so for our purposes, super small intervals and the exact rate function are indistinguishable. Okay, can we buy that? Having super small intervals and doing constant rates, or having the actual changing rate function, same thing, indistinguishable. So if the height of the flag at time 0, say it's a 5-meter flagpole, not very tall, but we'll just go with it. Right? Suppose the height of the flag at time 0 is 5. So over here, different graph now. So this was what? This was our rate of change for x, and what was our unit for time? Seconds?
Month.
No, this is the flag.
Oh. Seconds.
Yeah, that wouldn't be fun, would it? Okay. All right, so we still got x in seconds, but instead of rate of change on the right graph, we want to now look at just the height of the flag. Height of the flag. Or this is our amount. In this case, height of the flag. All right, so I want you to, can you sketch based on a pretend rate function with really small intervals or the exact rate function, can you sketch what the amount function or the height of the flag function looks like? So work with somebody next to you. See if you can make a sketch, and then I'll turn it on and you see how close you were. Okay. Right, yeah, so in between when it's changing hands, we get this kind of a small period of time where the rate slows way down, like almost like to zero for a moment, and then the next pull, right? And then in between this thing going down, we have something like that. Is that what you drew? Yeah. So it's heading down, but then there's these moments where it pauses, right? There's a pause, and it's not going down, and then we see that rate of change being zero, or very close to zero. Okay, so let's look at from, say, 0.5, starting at 0.5 seconds, to, I don't know, 1.8 seconds. So starting at 0.5, 1.8 seconds. Okay, first of all, I'm going to highlight those points. I don't like that, so let's do 0.7. And then similarly, let's look at same interval over here, 0.7 to 1.8. So I got 4 points. Not this one. Okay, so 4 points. I want you to tell the person next to you, have a conversation, the meaning of those 4 points. So it's 1, 2, 3, and 4. What's the meaning of each of those 4 points? So maybe take turns going back and forth. Explain the meaning of those 4 points that I highlighted on the graphs. Go.
That time it's at a constant rate.
During that time, does that point mean a duration of time? Does that point mean a duration of time?
Exact time.
Yeah, so what exact time is it?
0.7.
Okay. And it tells us, that point tells us that we have a rate of? Right.
To be precise, of 0.7.
Okay. Yep. So point A means that at 0.7 seconds, the rate of change is, and we're assuming negative 0.75. But then if we want to use function notation to express that, the coordinates would be? Go ahead. 0.7. What's that?
No, it's not negative. So it's just
F of 0.7.
Or what is it?
What's that?
Why is it not?
The value itself is negative. But still.
Yeah, it is a negative value, and that's what you get when you plug 0.7 into that function.
I see. You don't need the
Yeah,
negative
we
sign.
don't
The function tells us that the outputs of this function are negative. So that's what we're using. Okay, so next one, 1.8. And let's see. What right here? What's your name? Shauna? What about, can you interpret the meaning of point B?
So rate at 1.8 seconds.
Okay, so it's two numbers in combination, right? So at 1.8 seconds, it's the rate of change. And can you use function notation? What that would be?
1.8.
That's it. Right, so if function notation gives us the output, then it's which value on the graph? X or Y?
Why bother?
Yeah, so output values of a function are y values, so we can use function notation to express y values. That's what we're doing. Okay, how about over here? Point C. How about Patrick?
So point C coordinates are 0.7 and then like big F of 0.7.
And what does the point mean?
And that is the position with the corresponding point A, because point A is just the slope at that given moment of point C.
Okay. So does the point mean the position? What does the point signify? So the point means what? What does the point C mean? Because you started off by saying it's a position. Is point C a position?
Yes.
Kind of. But it has to do with a position.
Right.
But what's its title?
Its position at a particular point in time.
Yeah, so given the time is 0.7 seconds is the corresponding height of the flag, right? So at 0.7 seconds, the height of the flag is, what estimated, what is it about? 4 point, something between 4.5 and 4.6, 4.55 maybe, as an estimate. Okay, yeah, but it's two quantities, not just one. The point represents two quantities, the time and the corresponding height. And then for D, what does the point represent? Point D. Tell me your name again. Yeah.
Joel?
Yeah, Joel? What does that point represent, point D? The height of the flag at 1.8 seconds. Yeah, at 1.8 seconds, it's 1.8 seconds and the corresponding height at 1.8 seconds. So the coordinates would be?
8 and 3 point, just a big 3.9.
So that 3.9 is an estimate, but how could we write that exactly? How could we write that height exactly?
Function of 1.8.
Yeah, capital F of 1.8. Okay, so that's just kind of review, warm up. So I want to write, there was a certain change of height of the flag between 0.7 and 1.8 seconds. So I want to write that change of height of the flag in two different ways, using the left side graph and using the right side graph. So I want you to write the change in height, write an expression. That computes the change in height of the flag from 0.7 to 1.8 seconds. And you want to do that for every single point. Well, how do we do that? We just talked about it.
Integrals.
Integral, right? Integral from we're summing up. So he's right. We're going to sum up every single little bit of change. And how do we do that? Integral from 0.7 to 1.8, but instead of discrete values of rate, we have the whole, every single rate, and instead of big delta x's, we have dx. So these are still, this is still bits of change. It's just, we like writing the integral rather than spending, years on end adding them up one by one. So we just write the integral, and that's what it means. Okay, so that's one way to express. So minus the caption. Okay? There's one way to express that. The other way is super easy. We should all be able to do the other way. So how can we write another way to compute the change in height of the flag from 0.7 to 1.8 seconds? Do you got it?
Capital F 1.8 minus capital F 0.7.
And can you explain why?
Because that function over there
Mhm.
equals capital F B minus capital F A.
Oh, so that's what we're developing. Okay, so yeah. But why does capital F 1.8 minus capital F 0.7 calculate the change?
The height of the flag at the final value
Right.
minus the height of the flag at the initial value.
Yeah. So this is how high the flag was at the end, right? And this is how high the flag was at the beginning. So how would you get the change? You subtract, right? You subtract. If it's 3.8 at the end and it started at 4.6, how would you get that amount of change? You take 3.8 minus 4.6, and that would be that amount of change.
So then you get the change for this one, you have to multiply 1.8 and f small f of 1.8, then take away f of 0.7 times 0.7.
Actually, I didn't hear the beginning, so I lost it before the beginning. Can you start over?
Yeah, I mean, to find the change, you need to multiply f small f of 1.8 by 1.8, then minus.
It's a change in
No, this is an integral. It's a discrete integral.
Are you talking about what we just did, or are you talking about what we did before?
No, I'm talking about this other side.
It's a change in rate. It's not constant.
Yeah, so the red is the change in rate, right? There's no constant rate. The red graph is this continually changing rate.
Oh, yeah.
Yeah.
Okay.
Okay, but back to this side. So over here, we got what? F of 1.8. Final height of the flag minus the initial. That's how you find the change in a quantity. Final minus initial. So then the two things I put a red box around, how do those compare?
They equate.
Are they, well,
Yeah,
what about the values of each of those?
it's the same.
Yeah, we're computing this is the same thing on both sides, right? So this is using the process of adding up all the bits of change, that's our integral, or just looking at the final height minus the initial height. That also computes the change in the height. So, conclusion? They're equal.
Oh, yeah, which takes us back to the
So now we're yep.
text back.
Okay, now there's one more. So this is the next principle: is that there's two ways to calculate the total amount of change: using the integral, using summing up bits of change, or just taking the final value of the quantity minus the initial value of the quantity. Two different ways to calculate an amount of change. So those expressions are equal. So the last question is, what's the relationship of the capital F function and the little f function? That's the last principle. How does the capital F function relate to the little f function? Can you tell me? What's your name?
Karen?
Karen? So how does capital F as a function relate to little f as a function? What's the relationship between those two?
Well, the little f function, those values are the slopes of the big F function.
Okay, so that would mean what?
So that means that
Little f is?
little f is the integral of big F, or no,
No.
the derivative.
Little f is the
Derivative.
derivative of big F, right? So if little f is the rate of change of this quantity, then it's the derivative function. Therefore, big F is the
Antiderivative.
antiderivative of little f, okay? So this is the rate of change of this. So it's little f is the derivative. Therefore, big F is the an antiderivative, right? There's more than, given a rate function, there's more than one antiderivative. So capital F is any antiderivative of little f. And that's it. That's the whole fundamental theorem. Questions on the flag example? Anything that I've got up there? Any questions? So let's summarize. So we said make more small intervals, Super small intervals give us the integral, the left side. Okay? So next principle. Oh, sorry. Principle 6. 2 ways to represent an amount of change. 2 ways to represent an amount of change. Using the rate of change function and integral, and using the quantity function or the amount function, just final minus initial. And then last principle is the quantity function f is the antiderivative, or a and quantity function f is a antiderivative of the rate of change function little f. Because little f is the rate of change of big F. So it's the derivative. Okay, so that's what's going on here. It only took us 2.5 hours. Okay? But that's the point. It's a rich thing. There's lots that goes into this, into developing and understanding that. It's not, this is the way you do some exercises and get answers, right? There's rich meaning all behind that, and we want to understand that. Okay, and so this notation down here, so just look at the second line, is what we're talking about. So we often write that as, just write the antiderivative function with this bar. X equals A is X equals B. It means exactly what I have in the red box. Okay? So this expression right here means evaluate capital F at B, evaluate capital F at A, and subtract. We're finding the change, the net change of that function as X goes from A to B. So it's just different notation. Okay, so you had problems like this, right? You had problems like this, and you were solving these and getting a number, getting an answer. But so now we want to take time to interpret what we're looking at. So when we look at that first expression there, the integral from 1 to 5 x to the 4th dx. I want you to take a second with your partner. Okay. What does this mean? So we want a full and complete, precise definition of what does that whole thing as an expression, what does it mean? Okay? See if you can hammer that out with your partner. Go.
Start it first.
X to the 4th, or graph about every line around 1
So this is
Okay, let's hear several of these, see how we did. Tyler first. So Tyler, that thing is what?
The value of the function x to the 4th from 1 to 5.
The value of the function of x to the 4th from 1 to 5.
No.
Well, let's hear some more. Dealing, okay?
Oh, it's the amount accumulated, starting at 1 and ending at 5 of the rate of change of x to the 4th.
She says the amount accumulated starting at 1, ending at 5 of the rate of change of x to the 4th. Okay, someone else in your own words. Go for it.
Can I sum that up as just simple displacement over that interval?
Displacement over that interval. Well, displacement is specifically like a change in position. And that, we could have any quantity here. It could be temperature, pressure, You know, like, so displacement is a very specific thing. So we don't know what the context is. By displacement, that, like in physics, displacement is like change in position. So it might be displacement. It might be displacement, but it could be something else too.
So given that x to the fourth describes some rate of change,
Okay.
this integral from 1 to 5 would describe the quantity on x within that interval.
Quantity on x within that interval.
So I guess being more specific, we could say that it's the area underneath this curve from 1 to 5.
Did we ever say area?
Not yet.
Yeah.
So quantity maybe
What's that?
quantity.
Is what? So
You just say what is the quantity of
the quantity of.
since x to the fourth is the rate of change.
X supports the rate of change.
Yeah, so then what you just want to find is the quantity, whatever it is, might be area, or might be temperature, might be whatever.
Okay.
Between 1 and 5.
The quantity between 1 and 5. What were you gonna say?
The exact amount of accumulation from 1 to 5 at the rate of change of x to the fourth over the interval to x, dx.
Okay. Anyone else want to try? So we have lots of good stuff coming out here.
Pretty good.
You want to try? Yeah.
It's the total amount of change from x equals 1 to x equals 5 when the rate of change is x to the fourth.
That was
Nice, dude.
nice. Total amount of change. So I just want to say of some quantity, say Q, as x changes from 1 to 5. Where Q's rate of change is x fourth. Of change. Sorry, total amount of change. So yeah, you can write this down and you can kind of memorize that form, but the more important thing is that you can say it in your own words. So it'd be a dozen or 20 ways to formulate that in your own words, and that's the key. And I'm not crazy about this. I just kind of went off what he said and then just added a little bit. And so this is the total amount of change in some quantity Q as x changes from 1 to 5, where Q's rate of change is x to the 4. Okay, and what is that total amount of change? Can you find that total amount of change? Find the value. This is a review from Calc 1. You should be able to do that. You should be able to find that total amount of change. Can't. Use the fundamental theorem. Don't add up a bunch of little bits of change. We only have 4 minutes left. So do it. That's right.
Plus a constant.
No.
Oh no, that's a discrete interval. Yeah. Yes.
Okay, what does the fundamental theorem say? So hopefully, fundamental theorem says that this is the same as.
That 1 over 5x f of b f of 5 minus f of 1.
So there's some quantity function whose rate is x to the 4th, and we're going to just take that at 5 and subtract that 1, because that's also the change of the quantity, right? This is a total change of quantity Q. Well, this is the total change of quantity Q if capital F is the function for quantity Q. All right, so then how is F related to x to the fourth? It's its antiderivative, which is?
1 over 5 x.
Okay.
And you just now substitute.
And so 5 to the fifth over 5, I think, is 5 to the fourth, right? Minus 1/5. 624?
624.
So 625 minus 1/5. 624 and 4/5. And 624.8 is what? What does that number mean? It's the rate of change?
Well, when you change the interval.
It's the amount, it's a certain value of quantity Q?
Yeah.
A certain value of quantity Q?
Yeah.
Not quite.
Change.
It's an amount of change of quantity Q. It's a certain amount of change. Starting at x equals 1 to x equals 5 at a rate of change of x to the fourth. So this is a delta y, right? It's not a y value, it's a delta y. Okay, so we got a long weekend.